In my earlier video, I had seen inner product induces a norm. Today's goal of this lecture is I will say different norms which are not induced by inner product. This is our first goal of this lecture. It is very interesting. Then our second goal, I will say different type of norm as a norm balls, and I will visualize norm on a unit circle. Okay? Now let's come back our original discussion. Euclidean norms, which measures the Euclidean distance of the origin in Rn from an point x. Thus, this is a measured length of the vector, which is defined as norm of x equal to square root of inner product x comma x. But today's goal of this lecture is about non-Euclidean norm. We shall define two important norms in Rn, namely first one norm and infinity norm. One norm is for any vector x in Rn, the one norm is defined as at first absolute every component, then add them. Geometry of one norm I will define few minutes later. Next norm is infinity norm. Infinity norm is given as max of absolute value of component, and these two norms are not induced by inner product. Now I will see different type of norm balls. First, Euclidean norms. We all of us know this is equal to square root of absolute value of x1 square plus absolute value of x2 square up to absolute value of xn square. Okay? And this notation is called as actually L2 norm. And if we define L2 norm balls, for this consider norm of, this is called 2 norm, always norm of x2 less than equal to 1, and this corresponds to circle or sphere in n-dimensional. Okay? Generalize of L2 norm is LP norm, which is equal to absolute value of x1 to the power p plus absolute value of x to the power p up to absolute value of xn to the power 1 over p. And when p equal to 2, then it reduces to L2 norm. Okay? Are you getting? This is actual Euclidean norm. Now I will say the norm ball of non-Euclidean norm. We all of us know now non-Euclidean norm means first one norm, which is actually denoted as sometimes L1 norm. Then the norm ball would be such type norm of x less than equal to 1, and consider R2, then the vector x would be x1 x2, this component. Then norm of x less than equal to 1 in L1 norm means from this expression this imply absolute value of x1 plus absolute value of x2 less than equal to 1, and these imply 4 cases. Consider x1 x2 greater than equal to 0. That corresponds to x1 plus x2 less than equal to 1. And this is actually the first coordinate. Next, consider the second quadrant. Here, consider x1 less than 0 and x2 greater than 0. And x1 less than 0 means absolute value of x1 would be minus x1 and x2 greater than 0 means plus x2 less than equal to 1. Then would be third quadrant. Okay. And in third quadrant, consider x1, x2 less than 0. And then this would be, since x1, x2 less than 0, then absolute value of x1 would be minus x1 and absolute value of x2 would be minus x2. This would be less than equal to 1. And in fourth quadrant, both x1 greater than 0 and x2 less than 1. Sorry, less than 0. That imply x1 minus x2 less than equal to 1. Are you getting? Well. Now if we want to draw L1 ball, then first would be x1, x2 greater than equal to 0, and that imply x1 plus x2 less than equal to 1. This is this line, x1 plus x2 here less than equal to 1 and x1 comma x2 greater than equal to 0. Okay, and this is the second quadrant, which is minus x1 plus x2 less than equal to 1. This imply this line. Then third quadrant would be minus x1 minus x2 less than equal to 1, and fourth quadrant would be x1 minus x2 less than equal to 1. This is the picture of L1 norm. Sometimes it is called 1 norm. Are you getting how look like the norm ball of L1 norm? Okay. And this type of norms actually more important for higher study. And notice L1 norm. For these ages, L1 norm not be differentiable. But L2 norm, since this is circular sphere, this is smooth. So obviously this is differentiable. So for calculus, L2 norm is very necessary part. Okay. So I will highly recommend you, please see this topic with pay attention, because this part actually not just basic part. This is important for higher study also. Now I will see the L infinity norm. Suppose now this is actually the maximum value of absolute value of x1 comma x2 comma absolute value of xn. Actually this geometry is limit p tends to infinity. Norm of x infinity is equal to limit p tends to infinity norm of xp, which is equal to limit p tends to infinity x1 to the power p plus x to the power p up to xn to the power p to the power 1 over p. And from this expression this implies this, since this is limit p tends to infinity. So this imply actually maximum of absolute value of x1, absolute value of x2, absolute value of xn. Are you getting the L infinity norm clearly? Okay. As for example, if we consider R3 and if we consider the vector 2 minus 3 minus 1, then L infinity norm is given by maximum of absolute value of 2 comma absolute value of minus 3 comma absolute value of minus 1. This is equal to maximum of 2, 3 comma 1, which is equal to 3. And the note is actually L infinity norm of a vector is called the maximum norm, which is actually the largest of the absolute value of all elements of the vector. Now notice how will be the graph of L infinity norm. Notice with attention, this is the L2 norm and L3 norm would be such type, and this norm is L5, this is L9, And notice one thing, when the value here has increases, then this is actually tends to square. So when p tends to infinity, then this would be L infinity. So this is actually would be the square. Now let's see unit circle of norm x1, norm x2 and norm x infinity. By previous idea, obviously this circle is norm x2. This is the unit circle in norm x2 and this cube is unit circle in norm x1 and this square be the unit circle in norm x infinity. Are you getting? Have you understood why in different norm the picture of unit circle be different? OA. And notice from this picture we can tell norm x1 less than equal to norm x2 and norm x2 less than equal to norm x infinity. Okay? That means unit circle for norm x1 is smaller than unit circle and norm of norm x2 and unit circle of norm x2 is smaller than unit circle of norm x infinity. That means in which norm the function is defined, this is more important. Okay? Let x be vector space over the field F. A norm on x is a function from x to R. We all of us know this is which satisfy some condition. Then the pair x with norm is called norm space. As for example, the norm with respect to one norm, two norm and infinity norm on the set, here the set is set of all closed interval on the set close 0 1, here the field is real number. That means the vector space of all continuous function from 0 1 to R. Here for this different norm, the norm will be different. Here the norm P is such type integration 0 to 1 absolute value of fx to the power p dx to the power whole power 1 over p, where p greater than equal to 1 less than infinity. That means here the norm 1 is defined as 0 to 1 absolute value of fx dx. Okay, norm 2 would be such type integration 0 to 1 absolute value of fx whole square dx to the power 1/2. And norm infinity is defined as maximum of the function absolute value of fx over the interval close 0 1. This is the norm infinity. Are you getting? Different type of norm space in the on the vector space set of all continuous over the interval close 0 1 on the field R OA. Now I will verify this will satisfy all condition of norm. Obviously this will satisfy, but I will verify because this verification is more important for any competitive exam. Which function be norm and which function be not norm. Let's verify this norm. To verify, at first consider two arbitrary function fx and gx belongs to the set x, where x equal to set of all continuous function on the closed interval 0 1. Then for a fixed value x belongs to close 0 1, absolute value of fx plus gx, we all of us know this is always less than equal to absolute value of fx plus absolute value of gx. And see, this inequality holds for all x belongs to closed 0, 1. Now, apply maximum in both inequality, because here the norm is defined as supremum or maximum. Since this is hold for x belongs to closed 0, 1, so this inequality will be hold for maximum values also. If we set apply maximum for all x belongs to closed 0, 1, also here apply maximum for all x belongs to closed 0, 1, then this means norm f plus g infinity, and this inequality means fx infinity, and from this inequality we can write this is the gx infinity. That means triangle inequality has satisfied here. Now I will see our second condition. Absolute value of alpha times fx always would be absolute value of alpha times absolute value of fx. Now apply max on this inequality to prove this function be satisfy all properties of norm. Apply max on the closed interval 0, 1 in both sides, then these imply norm alpha fx infinity, and just omit here this is scalar, so omit alpha from this expression, then this would be mod alpha times max of x belongs to closed 0, 1 absolute value of fx, and this is actually norm f infinity. That means this satisfy also the scalar condition. Now norm fx infinity is 0 function imply obviously by definition a maximum over the interval closed 0, 1 fx mod absolute value of fx equal to 0, and absolute value of fx equal to 0 means obviously fx equal to 0 function. That means all condition norm has satisfied here. So obviously this function be example of norm linear space. Are you getting how we have to verify any function be norm linear space? Now consider x equal to C1 close interval 0, 1. That means set of all continuous function over the interval 0, 1 with first derivative. Okay, here fx belongs to x, then norm f is defined as maximum x belongs to closed 0, 1 absolute value of df dx. Now my question, does this function define a norm? Just think. For this consider f be a constant function, then norm of fx obviously would be 0. Here notice I have considered non-zero function, but I have got norm f equal to 0 for all x belongs to closed 0, 1. That means condition of norm has broken here. So set of all continuous function on the closed interval 0, 1 with first derivative not define a norm. Are you getting how we have to define a norm linear space? This is more important for any comparative exam. Which space is norm linear space and which space is not norm linear space? This is more important for any comparative exam. So I will highly recommend you please see today's video with me. See some inequality of inner product space. First inequality, Cauchy-Schwarz inequality, and this inequality will satisfy those norms who is induced by an inner product. The statement is, suppose V is an inner product space, and consider arbitrary 2 vector in the vector space V, then absolute value of inner product V with W always less than equal to norm V times norm W, where this norm V is induced by inner product and this norm W is induced by inner product. Okay? Then obviously norm CB plus DW whole square, since this is norm, obviously this part would be greater than equal to 0, and this is equal to, we all of us know, inner product CB plus DW with CB plus DW, and apply distributive law. Then we all of us know inner product U with alpha V is equal to alpha bar times inner product UV. Then if we apply distributive law, then inner product CB with CB. Now apply this condition. If we consider this is complex field, then this would be C bar times C inner product V with itself. Similarly, from this relation, this would be plus C bar times D inner product V with W, then plus D bar times C inner product W with V, and then this would be D bar times D inner product W with D. And obviously C bar with C equal to absolute value of C whole square, and this is norm V square. Similarly, this means absolute value of D whole square times norm W square, and from this expression we all of us know Z plus Z bar equal to 2 real Z. That means from this expression this is equal to 2 real C bar times D inner product V with W. Okay? This is the first step 1 of our proof. Then I will choose different type of C and D to get nice inequality. Choose C equal to norm W and D equal to minus inner product W with W over norm W square. Now put the value here. Then C would be norm W square times norm V square, and put the value D here and D here. Then this would be reduces minus 2 real inner product W with V times inner product V with W plus absolute value of inner product W with V whole square. And we all of us know for real part inner product VW is always equal to inner product WV. So this would be just minus 2 absolute value of inner product W with V whole square. Then by this expression we can tell this is norm W square times norm V square minus absolute value of inner product W with V whole square. From this expression we can tell easily inner product V with W absolute value of less than equal to norm of W square times norm of V square. Okay? This is nice inequality. Relation between inner product with norm. If we apply this inequality on the standard inner product on the set of continuous function on AB, then by this inequality we can tell integration a to b fx gx dx whole square less than equal to integration a to b fx square dx times integration a to b gx square dx. By this inequality we can tell easily this part, but actually this is very hard to prove, this inequality. if we know this inequality, then we can tell easily by this inequality this is true. But if we want to prove this part, then this is very hard to prove. Furthermore, this equality holds if and only if the set VW is linearly dependent. Other nice property norm induced by inner product is triangle inequality. The triangle inequality implies, suppose V is an inner product space, then the arbitrary vector VW in the vector space V, here this norm implies norm induced by inner product, then norm of V plus W always less than equal to norm of V times norm of W. This inequality is called triangle inequality. Furthermore, equality holds if and only if V and W in the same direction. That means either V equal to 0, because when V equal to 0, then obviously this equality hold, or when W equal to CV, just put W equal to CV, then this equality always hold. And this proof is very easy type proof. Just try to own self. This proof is same as Cauchy-Schwarz inequality. Also, Cauchy-Schwarz inequality here also will be used. Just try to own self. This type of proof is very important. Now we will see other inequality of such norm which is induced by an inner product. The inequality is parallelogram law, and parallelogram law indicates norm x plus y whole square plus norm x minus y whole square equal to 2 times norm x square plus norm y square. This norm actually indicate norm induced by an inner product. Okay. Now I will see, in the beginning of the lecture I have seen all norm does not induces by an inner product. For this, consider LP where P not equal to 2. Obviously this is non-linear space, but this is not be inner product space. For this, consider the norm xp as such type summation I equal to 1 to infinity xi to the power p to the power 1 over p, which is less than infinity, where x equal to set of all sequence x1, x2, x3 dot dot dot. That means LP is such type set of all sequence such that series converges. This, consider x equal to 1 1 0 0 0 belongs to LP and y equal to 1 minus 1 0 0 0 also belongs to LP. Then norm x equal to summation I equal to 1 to infinity absolute value of xi to the power p to the power 1 over p. This is actually equal to the power 1 over p. Similarly, norm y equal to the power 1 over p, then x plus y would be equal to 2 0 0 0, which is obviously belongs to LP. Then norm of x plus y with respect to p would be 2 to the power p to the power 1 over p. This is equal to 2. Similarly, norm of x minus y would be 2. Then notice the left hand side of parallelogram law. Norm of x plus y whole square plus norm of x minus y whole square. This would be 4 plus 4. This would be 8. And right hand side of the parallelogram law, 2 times norm of x whole square plus norm of y whole square. Just put the value. Norm x means 2 to the power 1 over p and norm y means 2 to the power 1 over p. Just put the value. 2 times 2 to the power since this is norm of x এর whole square, this means 2 to the power 2 over p plus 2 to the power 2 over p. This is equal to 4 times 4 to the power 1 over p. When p not equal to 2, then these two values are not same. When p equal to 2, obviously then this value would be 8, then this is equal to same. But when p not equal to 2, then left hand side not equal to right hand side. That means parallelogram law here does not satisfy. Therefore, this norm does not induces by inner product, because when parallelogram law will be satisfied, then that imply norm induced by inner product. Have you understood why I have told you in the beginning of the lecture all norm does not induces by inner product? Oh well. Today I will stop here. In my next video I will again discuss inner product space. But at first I will highly recommend you, please see today's video with pay attention, because this topic is very important for competitive exam. See you soon. Stay safe and stay positive always. And don't forget to do subscribe my channel. Thank you so much.